You know when you see a messy, kind of pixelated image, and you wonder how a computer could ever clean it up? Well, today, we're going to dive into some brilliant techniques that teach computers how to see, not just in pixels, but in actual shapes. It's pretty cool stuff.
So, first, let's set the stage and look at the core problem we're trying to solve. Digital images, especially after a computer has already had a first pass at them, can get really noisy.
Okay, check this out. This is supposed to be a fingerprint after a computer tries to isolate it from the background. That's a process we call segmentation. We're left with, well, this mess. You can see the main ridges, sure, but you've also got these random white pixels floating around, and you've got black holes breaking up the ridges themselves. If a computer's trying to get an accurate match, all this noise is a huge problem.
And that brings up a really fascinating question, right? How in the world can a computer clean this up? I mean, it doesn't have a clue what a fingerprint or a ridge is. To the computer, this is just a grid of ones and zeros, pixels that are either on or off. So how does it possibly know which ones to keep and which ones to get rid of? Well, the answer is a set of techniques that can turn that mess into this. Just look at the difference. On the left, you've got the noisy original, and on the right, you get this clean, crisp image after what's called morphological processing. All those stray dots? Gone. The ridges? They're solid now. It's a night and day improvement, and we're about to break down exactly how this magic actually works.
To really get this, we've got to stop thinking about individual pixels. We need to start seeing the image in a completely different way.
And that brings us to the key idea here, morphology. In the world of image processing, morphology is all about analyzing an image based on the shape of the things inside it. It's a huge shift in thinking. We're not asking, hey, what color is this one single pixel? Instead, we're asking, what kind of shape is this whole cluster of pixels a part of? And the number one goal is to use this shape-based analysis to get rid of all those imperfections we saw in the fingerprint. It's basically a cleanup tool that works by understanding structure, not by understanding what a fingerprint is. Okay, so how does a computer actually analyze these shapes? Let's get into the basic toolkit. It all comes down to a few core ideas that are honestly pretty simple, but they are incredibly effective. The main tool of the trade, the absolute heart of morphology, is the structuring element. The easiest way to think about it is like a tiny magnifying glass or a little probe. It's a small grid of pixels that the computer just methodically slides over every single part of the main image, testing the neighborhood of pixels around it. Now, as this little structuring element moves around, it's performing one of two key tests, a fit or a hit. A fit is the really strict one. For a fit to happen, all of the on pixels in our little pattern have to land perfectly on top of on pixels in the image. A hit, on the other hand, is way more relaxed. It just needs any one of its on pixels to land on an on pixel in the image. And trust me, knowing the difference between these two is absolutely crucial for everything that comes next. So, with that in mind, let's look at the first of the two big operations that uses these ideas. It's called erosion, and it's all about that super strict fit test. Just like the name implies, erosion is all about making things smaller. It systematically just eats away at the edges of the bright objects in an image, which makes them shrink or get thinner. Here's how it works, step by step. For every single pixel in the image, the computer centers its little structuring element right on top of it. Then it asks one simple question, do I have a perfect fit right here? If the answer is yes, that pixel in the middle gets to stay on in the new, cleaned-up image. But if it's not a perfect fit, even by one pixel, then that center pixel gets turned off. It's erased. It's eroded. And you can see exactly what that looks like right here. We start with a nice, thick letter A. After one round of erosion, it gets a little thinner. After another round, it's thinner still. You can see how the operation only eats away at the boundaries of the shape, kind of like how the ocean wears down a coastline over time.
Now, this whole shrinking idea might sound a little basic, but what you can do with it is incredibly powerful. Let's see how it solves some real-world image problems.
This is a fantastic example. What we've got here is a microchip with these really thin connecting wires. Now, because those wires are thinner than our structuring element, that element can never get a perfect fit when it's centered on any part of the wire. And the result? The erosion process completely erases the wires, but leaves the bigger, main blocks alone. It isolates the important parts perfectly. It's also amazing for smoothing things out. Look at the circle on the left, it's got all these little jagged bits sticking out. Since those little extrusions are small and thin, erosion just chips them right off, leaving behind the much smoother, slightly smaller circle that you see on the right. This is the exact same idea used to get rid of all that pixel static on the fingerprint.
And here's one more really clever use. Sometimes, in an image, two objects that are supposed to be separate accidentally get joined together by a thin little bridge of pixels. On the left, you see these two shapes touching. Well, if you apply erosion, it shrinks both of them, and that thin connection point is the very first thing to get erased, which splits them back into two distinct shapes. Pretty smart, right?
So, to wrap up erosion, it's an incredible tool for cleaning things up. It can split objects, strip away noise, and smooth out boundaries. But, and this is a big but, it has one major side effect. It shrinks everything. The important object you want to keep gets smaller right along with the noise. Now, this is where its counterpart, another operation called dilation, comes into play. Dilation does the opposite. It grows objects. It's perfect for filling in those little holes inside the fingerprint ridges. And by using erosion and dilation together, you can clean up an image without changing its overall size.
So what we've seen is that morphology gives a computer a really powerful way to understand shape. Simple tools like erosion can shrink things to remove junk on the outside, while its opposite, dilation, can grow them to fill in holes on the inside. By combining these, we can teach a computer to clean things up with amazing precision. And that really is a huge foundational step in the much bigger journey of teaching a machine not just to see, but to truly understand.